Imagine carrying a bag that weighs as much as a small child. Now imagine that same bag holding together a skyscraper, a bridge, or an entire city. Most people see a cement bag for only a few seconds at a construction site, but almost nobody asks how that humble package survives rough handling, crushing weight, dust, moisture, and journeys across continents. And this is where it gets truly extraordinary. Think about this. More than 4 billion tons of cement move around the world every year. Yet before any cement reaches a mixer, it must survive inside a carefully engineered bag. A single failure can spill thousands of dollars of material, delay projects, and create dangerous conditions. What happens next surprised even experienced engineers. Today, we're following the hidden journey of a cement bag from raw material to finished product. You'll see giant paper mills, high-speed printing presses, automated tube-forming machines, precision quality inspections, and packaging systems moving faster than the eye can track. By the end, you'll never look at a cement bag the same way again. Most people never think about this, but a cement bag begins in a forest long before it reaches a factory. Much of the kraft paper used in cement bags comes from sustainably managed forests in countries such as Sweden, Finland, Canada, Brazil, and the United States. These forests supply long softwood fibers that create exceptional tear resistance. Some fibers travel more than 8,000 kilometers before reaching the converting plant. The secret lies inside the wood itself. Long cellulose fibers from softwood trees measure several millimeters in length, creating a natural network that locks together like microscopic ropes. Paper engineers carefully select fiber blends with purity levels often exceeding 95% cellulose. That structure helps the bag survive impacts that would tear ordinary paper apart. The logs arrive at giant pulp mills where rotating debarking drums strip away bark. Massive chippers reduce trunks into uniform with chips. Those chips enter digesters where heat, pressure, and chemicals separate cellulose from lignin. The smell of fresh wood mixes with steam as thousands of tons of pulp emerge every day. But here's what nobody tells you. Cement bags often contain multiple paper layers. Some premium designs use 2, 3, or even 4 plies. Each layer serves a different purpose. One provides strength, another improves print quality, while specialized coatings help resist moisture during storage and transportation. Next comes another hidden ingredient, industrial inks. Pigments arrive from chemical suppliers across Europe, Asia, and North America. These inks must resist sunlight, abrasion, humidity, and rough handling. Some logos remain visible after months exposed to harsh outdoor conditions. Adhesives also play a critical role. Specialized industrial glues bond layers together while maintaining flexibility. Engineers test formulations under extreme temperatures, ranging from freezing winters to scorching desert heat. A weak adhesive could cause catastrophic failures during filling operations. Then comes transportation. Giant rolls of kraft paper weighing up to 3 tons travel by truck, rail, and ship. Forklifts carefully move these enormous cylinders through warehouses. Every roll represents thousands of future cement bags waiting to be manufactured. Environmental pressure has transformed the industry. Modern manufacturers reduce material usage, increase recycled content, and improve fiber efficiency. Some facilities recover energy from production waste and recycle processed water repeatedly. Yet, one enormous challenge still remains. How do factories transform giant paper rolls into thousands of perfectly engineered cement bags every single hour? The transformation begins with giant rolls of kraft paper entering the bag manufacturing line. Some rolls weigh more than 3,000 kilograms and stand taller than a person. Automated lifting arms position them with millimeter precision before the machine starts. As the line comes alive, the deep hum of motors fills the factory floor. The paper unwinds at speeds reaching 150 to 300 meters per minute. Powerful tension control systems continuously adjust force to prevent wrinkles or tears. Sensors measure paper movement hundreds of times every second. Even a tiny deviation can affect thousands of bags downstream. Next comes printing. Flexographic printing presses transfer logos, safety instructions, batch codes, and branding onto the paper surface. Printing cylinders rotate at hundreds of RPM, while precision ink systems deliver exact quantities of pigment. The rhythmic sound of synchronized rollers echoes throughout the facility like a giant mechanical heartbeat. What happens next surprised even experienced engineers. Multiple paper layers merge together into a single structure. Industrial adhesives spread in extremely thin coatings measured in grams per square meter. The bonding process occurs in seconds, yet the resulting structure must survive loads exceeding 50 kilograms for months. As the laminated sheet moves forward, tube-forming stations begin shaping the material. Mechanical guides fold the paper into a cylindrical form, while adhesive seams lock the structure together. Machines perform these folds at astonishing speeds, often producing more than 120 tubes every minute. To the human eye, the motion becomes almost impossible to follow. The freshly formed tubes enter cutting stations where rotary knives slice them into exact lengths. These blades spin at thousands of revolutions per minute. Computer controls maintain tolerances within a few millimeters. Every cut must match the filling equipment that customers use later. Now the bottom forming process begins. Folding arms, vacuum systems, and adhesive applicators work together in perfect synchronization. Heated glue systems typically operate between 160 and 190 degrees Celsius, or about 320 to 374 degrees Fahrenheit. The smell of warm paper and industrial adhesive fills the air as each bottom seal takes shape. Some bags receive valve openings, one of the most ingenious features in modern packaging. These self-closing valves allow cement to enter rapidly during filling while reducing dust release. Engineers carefully design every fold and angle. Most people never notice this tiny detail, yet it dramatically improves efficiency at cement plants worldwide. The bags move through drying and curing sections where adhesives stabilize. Airflow systems regulate temperature and humidity to ensure consistent bonding. Depending on the design, curing may take several minutes before the bags advance. During this stage, thousands of bags flow through the line, like an endless river of engineered paper. Finished bags emerge at astonishing rates. Advanced production lines can exceed 20,000 bags per hour. Robotic stackers align them into perfectly organized bundles, while conveyor systems transport them toward packaging stations. The entire operation looks less like a factory and more like a carefully choreographed mechanical performance. But here's the mystery. Producing thousands of bags every hour means nothing if even a small percentage fail under real-world conditions. So how do manufacturers guarantee that every bag can survive crushing loads, rough transport, moisture, and the demands of construction sites around the globe? That's where the most advanced technology in the factory takes over. The moment a cement bag leaves the production line, a second battle begins. This isn't a battle of speed. It's a battle of perfection. Modern factories inspect thousands of bags every hour, searching for defects so small that most people could never spot them with the naked eye. Above the conveyor belts, high-speed cameras capture detailed images of every single bag. Some vision systems analyze hundreds of images per second. Artificial intelligence compares each bag against digital standards, checking print quality, dimensions, valve position, folds, and adhesive placement. The process happens faster than a human blink. Laser measurement systems add another layer of precision. Thin beams sweep across every surface, measuring dimensions with tolerances often below 1 millimeter. If a bag falls outside specification, automated reject mechanisms remove it instantly. The machine never gets tired, never loses focus, and never misses a shift. But here's what nobody tells you. Even the most advanced scanners cannot fully replace physical testing. Samples leave the production line and enter quality laboratories where engineers push them to failure. The goal isn't to avoid breaking bags. The goal is to discover exactly how much punishment they can survive. One test fills bags with loads matching real cement shipments. Hydraulic systems apply increasing pressure, while sensors record every change. Some testing machines generate forces equivalent to hundreds of kilograms. The paper creaks, the seams stretch, and engineers watch closely for the first sign of weakness. Drop testing follows. Bags fall repeatedly from control heights that simulate loading docks, trucks, warehouses, and construction sites. The impact produces a heavy thud that echoes through the testing area. What happens next surprised even experienced engineers. A properly designed bag can survive multiple drops without catastrophic failure. Factories also test environmental durability. Climate chambers expose bags to humidity levels above 90%. freezing temperatures below 0 degrees Celsius, and extreme heat exceeding 50 degrees Celsius. Engineers simulate months of storage in just a few days. The objective remains simple. Make sure the bag protects its contents under almost any condition on Earth. Defect rates in top facilities often remain below 1%. In some highly optimized plants, rejection rates drop below 0.5%. Achieving numbers like these requires thousands of sensors monitoring tension, alignment, adhesive flow, print density, temperature, and machine performance every second of the day. International certifications play a critical role as well. Manufacturers often comply with standards that govern packaging strength, dimensional consistency, environmental performance, and transport safety. Auditors inspect facilities, review documentation, and verify testing procedures. Every approval represents years of engineering discipline. And this is where human skill still beats machines. Experienced operators can sometimes hear subtle changes in machine sounds before sensors detect a problem. A slight vibration, a different rhythm, a nearly invisible shift in paper behavior. Decades of experience allow them to recognize issues that software may not yet understand. By the time a cement bag leaves a factory, it has survived inspections, measurements, stress tests, environmental challenges, and relentless scrutiny. Yet an even bigger story remains hidden. How many of these bags does the world actually use? The answer involves staggering numbers that are almost impossible to imagine. Now, let's zoom out and look at the scale of this industry. Every year, the world produces billions of cement bags to support construction projects across nearly every country on Earth. If you lined up just 1 year's worth of cement bags end to end, they would circle the planet many times over. Most people never think about this invisible packaging network that helps build modern civilization. The cement industry itself produces more than 4 billion metric tons of cement annually. That translates into an enormous demand for industrial packaging. The global market for industrial paper sacks and cement bags is worth billions of dollars every year. Behind every major building project stands a hidden army of packaging manufacturers working around the clock. China remains the world's largest cement producer, accounting for more than half of global output in many recent years. India follows as a distant second, while countries such as Vietnam, the United States, Turkey, and Indonesia contribute significant shares. Together, these nations consume staggering quantities of cement bags every day. Entire factories dedicate their production exclusively to serving these massive markets. Think about this. Millions of workers worldwide depend directly or indirectly on construction materials and industrial packaging. From forestry operations and paper mills to logistics networks and manufacturing plants, an enormous workforce keeps the system moving. A single cement bag may pass through dozens of hands and machines before reaching a job site. The history of cement bags stretches back more than a century. Early cement shipments often relied on simple sacks that lacked modern durability. As cities expanded and construction projects grew larger, manufacturers developed stronger kraft paper designs, better adhesives, and more efficient filling systems. Today's bags represent decades of engineering evolution, hidden inside a product many people barely notice. Over the last 50 years, production speeds have increased dramatically. What once required large teams of workers can now be accomplished by highly automated systems. Modern lines produce tens of thousands of bags per hour with remarkable consistency. The combination of robotics, sensors, and computer control has completely transformed the industry. And this is where it gets truly extraordinary. Researchers are developing stronger fiber blends, lighter paper structures, improved moisture barriers, and more sustainable production methods. Some future designs may use significantly less material while maintaining the same performance. The goal is simple but challenging: reduce environmental impact without sacrificing strength. Did you know that a modern cement bag can survive forces that would instantly destroy ordinary shopping bags? Did you know some production lines manufacture enough bags in a single day to supply an entire city's construction projects? And did you know that tiny changes measured in fractions of a millimeter can determine whether a bag passes or fails quality testing? What looks simple on the outside hides remarkable engineering underneath. Over the next decade, growing urbanization, infrastructure investment, and sustainability goals will continue shaping the future of industrial packaging. Manufacturers will likely rely on smarter automation, advanced materials, and data-driven quality systems. The humble cement bag may look familiar, but its technology continues to evolve faster than most people realize. We've traveled from forests and paper mills to printing presses, robotic production lines, testing laboratories, and global supply chains. Along the way, we've discovered that a cement bag is far more than a simple container. It is a result of engineering, logistics, materials science, automation, and human expertise working together with astonishing precision. Most people see only the finished product stacked on a pallet or sitting beside a construction project. But now you know the hidden story. You know about the fibers harvested thousands of kilometers away, the machines operating at incredible speeds, the engineers testing every detail, and the technology protecting every shipment. What seemed ordinary has become extraordinary. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.